So I was saying there's a certain element of fragmentation in hydrology, and there are not so many studies where all the hydrologists of the world work on one particular scientific problem. But one group calibrates their model in their catchment, and another group they do their subsurface analyses and erosion, etc., with not as much coordination as it is, for example, in the climate science or in ecology. In ecology, it's very clear biodiversity is a good thing, so we need to all contribute to more biodiversity. And in climate science also, there's a very clear mission, and our mission is more fragmented, which has to do with a number of reasons. One of the reasons is certainly the education. We have hydrology education, geography, engineering, geology, etc. One of the reasons is that the hydrologic processes that are interesting for practical reasons are often spatially limited, so don't span the entire globe. And there are maybe other reasons that are more cultural within the community of hydrology. So there's fragmentation, as I'm showing here, in terms of processes, spatially, and also in terms of the methods. And I think it would be a good thing to overcome that fragmentation, more synergies, more syntheses within hydrology. And there are a number of ways of doing that, through collaborative projects, through education, also coordination of the journals, and also setting a community research agenda. And the community research agenda is what I'm talking about today. It's really setting a community research agenda. Previous efforts of agenda setting have been more limited, just involving small groups. There have been a number of attempts of doing that, mainly national, not so many international ones. And this particular initiative, UPH, Unsolved Problems in Hydrology, has been inspired by David Hilbert. He was a German mathematician about 100 years ago. He was a genius. And this is this gentleman. And in the year 1900, at the turn of the century, between the 19th and 20th century, he published a paper and presented it at the Congress of Mathematicians in Paris about 23 unsolved problems in mathematics. And problems not in the sense is how can we supply water to the city of Paris, but mathematical problems, research problems, proper research problems. And he encouraged the community to work on these 23 problems. And this is the reason also why we selected 23 for the case of hydrology, but Hilbert had 23 problems. It happened to be 23 problems. Okay, and here is just a screenshot from Wikipedia of some of Hilbert's unsolved problems. For example, the 9th problem, find the most general law of the reciprocity theorem in any algebraic number field. I don't know what it means, but mathematicians, I'm sure, will understand that. But the important thing here is the color code on the right-hand side. Green means resolved. Number 10, for example, has been resolved in 1970. This 70 years after he had proposed this problem. And the 12th one is still unresolved, so still more food for thought for mathematicians. That this is the context, that what has inspired us to do something similar in the discipline of hydrology. Okay, so an initiative in hydrology, what would be unsolved problems in hydrology that would foster the research in the next century? And these problems should be universal. So not what is a runoff coefficient in my favorite catchment. So that's not a universal problem. So it should be related to phenomena. Why does something happen? Which would be like the equivalent to mathematical problems. And they should be specific. And unfortunately, our problems are not as well defined as they are in mathematics. So We usually cannot even talk about solving a problem in hydrology, but we usually address a problem because boundary conditions are not well defined and catchments are not as comparable as we would like them to be. But still, I thought it would be worth an attempt. So increase the coherence of the community, energize the community, and speaking with one voice of the three main purposes to go from the fragmentation to the accumulation of knowledge. This is a picture taken from the Predictions in Ungauged Basin book published by Cambridge University Press 10 years ago. If you're interested in predictions in ungauged basins, this is a recommended reading, I would say. Okay, the UPH Unsolved Problems in Hydrology initiative was launched in 2017 in Port Elizabeth, South Africa. And you can see here Hubert Savenay on the stage, and where we started the initiative. And we envisaged a workflow of the initiative in 7 steps, starting with a video launch that was published on the internet. Then we had online discussions in a LinkedIn group. Then we had a number of personal meetings. This was pre-COVID, of course. Then we had a symposium in Vienna, one of the Vienna Catchment Science symposia. We have a tradition of running them after EFU in Vienna at my university. This year, we don't have a catchment science symposium. This year, we are running a symposium on the next decade of IAHS, which will be helping. Step 5, a synthesis and addressing biases of this discussion process, final consultation and publication as a paper. So these were the 7 steps. And here's a screenshot of the video launch, just explaining essentially what I'm saying now as a video message. And step 2, a screenshot of this discussion process in LinkedIn, and then the physical meetings, 2 splinter meetings at EGU, and this is the Catchment Science Symposium at my university. We had a very good participation, as you can see. And the nice thing, I think that the thing that most participants appreciated very much is that we voted on the question. So we had the procedure of classifying the proposed unsolved problems into gold, silver, and bronze. And then we voted the priority of the questions, whether they should be a gold question, silver question, bronze question, and we merged some of the questions, we split some of the questions. So this is the voting process, because it's a community initiative. And that as part of the steps, we had generative activities. Generative means creating ideas, brainstorming, steps 2 and 3. And then we had consolidation activities, contraction, which means brainstorming is not enough. You want to organize your thoughts, otherwise you are left with a chaos. Both is needed. Creative, in creating knowledge, information, ideas by a community, but then you also need to organize them and consolidate them. So we had these 2 elements in the process. And here comes the list of the 23 unsolved problems. We organized them into a couple of groups, 23 into 7 or 8 groups. The first one is time, variability, and change. And the first question reads, is the hydrological cycle regionally accelerating or decelerating under climate and environmental change? And are there tipping points, irreversible changes? Then how will cold region runoff and groundwater change in a warmer climate, and so forth? So these 4 questions belong to the group of time variability. And then the idea would be to address more than one group around the world the same question and mentioned even in the journals. This paper addresses science question number 1 of the unsolved problems in hydrology. And then if others read this paper, they can more easily link to the particular findings of that paper. First group, time, variability, and change. Second group is space variability and scaling. What causes spatial heterogeneity, catchment scales law, preferential flow, the residence time of streams. Then we have variability of extremes. Do flood-rich and drought-rich periods exist, and why? Then sensitivity of hydrologic extremes, and one more specific question on rain on snow events. Interfaces in hydrology. What the processes that control hill slope, riparian, stream, groundwater interactions, flows across boundaries, persistence of water quality, and the relationship with health. Measurement of data, measurement and data. So how can innovative technologies of measurements? And the question 16 is a nice example, actually, where the initial proposed candidate question was quite specific. It said, how can we measure subsurface fluxes? That was the question. And this is a very clear focus question, difficult to solve, but I think something that would be worth to join forces to further measurement methods of groundwater flux, not just water level, but flux, not just pressure, flux. But then in the discussion process, there is a tendency, because of the democratic process, of enlarging the question. And so many of the questions turned out to be less specific than the candidate questions. And this 16 is an example of that. It's a bit generic. 17, soft data. 18, socio-hydrology. And then we have 2 questions on modeling for changing conditions and uncertainty. And the final 3 are about interfaces with society, water, energy, food nexus, uncertainty and communication, and then something about water and people. Okay, so these are the 23 problems, and I would now like to show you a couple of slides about my personal interpretation of the process and the outcome of the process. These slides are not a direct outcome of this community process, but it's my interpretation of the thinking that was underway during these processes, so the lessons learned. And one of the lessons learned from my perspective is there's a need for more high-risk, high-gain activities. You may remember Wegener's theory of continental drift was questioned at the times of Wegener. It was not readily accepted. It was initially refuted. It's only after Wegener's death that it was really accepted. Because it was an outrageous hypothesis. People didn't really believe that the continents would float around on the surface of the globe. It was unthinkable. So, and perhaps we need more out of these outrageous hypotheses, more high risk and more high gain activities. European Research Council is a funding initiative at European scale that actually funds high risk, high gain ideas. And the pictures here are to illustrate the effect of the co-evolution of the landscape with hydrologic response. On the left-hand side, a catchment in Austria that has slow response with little erosion, where the response is dampened and the landscape is flat. On the right-hand side, high erosion, fast response, the co-evolution of hydrology and landscapes. So this is an example of the river network of these 2 regions. The left one is the Gurk and the right one is the Buwe region. differences in the stream network, difference in the landform have to do with the hydrology. Coevolution is the topic here. So a question here is, what are the feedbacks in the critical zone? Is another of these high-risk questions. And as an example, I'm showing here the indoor laboratory of Peter Droch in Tucson, Arizona, where they operated artificial hill slopes undercover in a building and looked at how the soil evolves with biochemistry and erosion, etc. So coevolution, I think, is an interesting question. Now, another lesson learned is that generalization is important. Open data models is directly related to synthesis. So not everybody should work in their own backyard. We should work better together, including spatially across different continents, across different catchments. And one way of doing that is comparative hydrology, meaning learning from differences in the hydrology in different places. And publications could refer to one of the 23 problems, as I mentioned already. And open data, I think, is one of the keys to a successful cooperation. And there are already some initiatives underway for making hydrological data of different countries available globally to all the hydrologists of the world. Food, water, energy nexus, an example again of a global scale analysis. Planetary boundaries, how food, water, energy interact, in global scale perspective. And here is an example of comparative hydrology to encourage this synthesis across processes, places, and scales. You see here the title page, cover page of the PUB book, runoff predictions in ungauged basins, synthesis across processes, places, and scales. An example of this comparative approach of the performance of runoff simulation in different parts of the world. So these black countries are countries from which data have been used to compare different methods of predicting stream flow in catchments where we have no measurements, stratified by the climate, arid, tropical, cold, humid. And as you see, as we go from arid to humid climates, the performance of the models increase. This is not a finding that applies to one particular catchment. It's a global finding. This is a kind of finding that unifies the entire community, or at least part of the community that is interested in this kind of predictions, but globally, not just in one country. And this is the essential point here. Then a slide about new data, big data, human sensing, of course, citizen science is also a very timely topic and it has a lot of potential. Data mining methods, new technology. This is an example of a rain sensor that was developed, I think, in Germany, that is low cost. So it costs a couple of euros and it can be multiplied. So we can use many of these things, as thousands, hundreds of thousands, because they are so cheap. One of the many ideas, but of course there are many different ideas of innovative data and of citizen science that do not necessarily follow the tradition of hydrologic measurements, few gauges, few instruments, very expensive, but there are also other possibilities. Okay, lesson learned 3 about the synthesis. The figure on the left shows a rendering of the perception of how hydrology has evolved in the 20th century. So at the beginning of the 20th century, most hydrologists would say, my field of expertise is water engineering, or science of water, and maybe even geotechnics. So the most expert had a very broad expertise. And over the course of the 20th century, we got more specialized, which is of course very understandable because our knowledge base increased exponentially. So we have much more information now than what we had 100 years ago. But then there is also a risk of this certain fragmentation. Some people only working in remote sensing, some people only on stochastic, some people doing just field people and saying, well, we are field people, you are modelers, we need to collaborate. But to my mind, this is the wrong approach. To my mind, we should all have a broad view in hydrology. We should be specialists about one particular method. We all have our pet methods, but have enough breadth to also embrace hydrology as a whole. So this is a vision of hydrology that is more synthetic, not so much split into individual branches. Okay, then a slide about water health nexus. I think water health is a topic that will increase continuously in importance as health is becoming more important. As humankind is aging. A slide from my own doctoral program I'm running in Vienna. There's a group working on water and health. One of the former students here, Margaret. And a slide about socio-hydrology, interplay of humans and water, a causal loop diagram that represents a simplified representation of the feedbacks in the system, in this kind of feedbacks of humans and floods from a long-term perspective. Again, a broader view. And some examples of that we not only can simulate water level, but we can also simulate the flood risk awareness of the people, and we can simulate to which extent people will, with some likelihood, build dams in the future or retain water in the landscape. That's a broader view, and I think also timely for the 21st century. Okay, conclusions. We live in the Anthropocene, so the topic of change was, of course, paramount in the entire UPH initiative. All the questions focused on the process-based understanding of hydrological variability and causality. Increased attention to change and interfaces, feedbacks central to all of that. And okay, and that this is a screenshot of the paper that was published 2019, almost 4 years ago. And as you can see, it has already more than 60,000 views, 350 citations, and a long list of authors. So what is it good for now? The question is, of course, how can it be used? COVID had a bit of a incision on the sharing and the distribution of the results of this initiative, because COVID started just at the end when it was published, the paper that interrupted the dynamics of this initiative a bit, but it's now slowly taking pace. And here are a couple of avenues that can be pursued and are already being pursued to strengthen hydrology, to increase the synthesis of hydrology in different domains. The first one is organized conference sessions according to the UPH, and the RAHS is already doing that, for example, in Berlin in July this year. Second, organized projects according to UPH, and some people are already doing that. So saying, my project proposal is about one particular science question of the UPH. Then the third point here, community meta-analysis. So here's one example of my own publication with a group in South Africa. Community meta-analysis, I think, is something that is not very hard to do, and we do not have a very good tradition in hydrology of doing that. Other disciplines, for example, the medicine or ecology, have a much stronger tradition of doing meta-analysis. where there's a regular tradition, like every year, every other year on one particular topic of pulling together all the knowledge that exists on one particular science question. The role of one particular medication, the success of one particular chirurgical method. We have a weak tradition of doing that. And I think this would not be hard to do. It requires a lot of thinking. It doesn't require so much money. It doesn't require material and funding for field work and data analysis, not so much, but going through the literature, it requires a lot of thinking and talking with each other to find what is the community consensus based on evidence published in the literature on particular questions. So one idea would be a meta-analysis of UPH number 1, meta-analysis of UPH number 2, etc. This would be an idea. I think it would be worth pursuing and would very much strengthen hydrology. Then an initiative I've myself been leading over the last 10 years, all contributing to the synergies of hydrology, because UPH is only one of the initiatives I've contributed to enhance the compaction and the cooperation within hydrology. So this particular initiative has to do with our journal publications. I've been organizing meetings of editors of hydrology journals across all the publishing houses. There are a total of 20-25 hydrological journals at the international scale. And so I invited the editor of these journals, and we had meetings every 2 years. And some of the meetings we published a joint editorial as an output of these meetings. This is one of them. And that conveys the message of the editors, how the editors feel, the potential of the community from an angle of the journals should pursue, or what the risks are of the community, what could be improved. So these are really opinion pieces of the editors of all of these journals. Maybe worth to have a look at them if you're interested in the role of journal publication in fostering the progress in hydrology. And UPH also play a role in these discussions, because they could be one vehicle of more coherence or more connections between the journals. For example, it would be possible to add a note to all the hydrology journals mentioning what UPH this particular paper contributes to, if any. And then the last one here on this list, community data sets. I think this is also very important for the coherence of hydrology globally. There's already some initiatives, for example, CAMELS initiative. Here is a screenshot of the CAMELS Chile initiative, but the also one in Brazil and a couple of other ones. And I think we need more of them. So the global community in hydrology has a data set available on which the community can work in a collaborative way. Okay, and that's it. I would like to thank you very much for your attention. I'm very happy to answer questions.